Hi friends, welcome back. Okay, so this is the last session for you. So in this session, we are going to see digital filters. So digital filter, what is a filter actually? It is a frequency selective circuit. Why it is used? It is used to reshape the waveform. That is the one thing, and it is used to eliminate some of the frequencies, and it is reserved to some of the desired frequencies. Understood? So what is this filter? Filter is frequency selective circuit. Filter is a frequency selective circuit. Frequency selective circuit. Why it is used? Used to reshape the waveform. Next, to select wanted frequency or desired frequency. Desired frequency. So this is about the filter. So digital systems we haven't seen. So I am just giving you somewhat information about the digital system. Uh, Classification of digital. You might see in the control system about the continuous time system. What is that? Suppose minimum phase system, maximum phase system, mixed phase system. These kind of words you might heard. So what is a minimum phase system? So for all the systems, we are taking the stable system only. Stable system is all the poles are inside the unit circle. Now I am talking about minimum phase, maximum phase, mixed phase. So let's say first for continuous time case you can understand, then you can see the discrete time. In the continuous time case, all the poles are left half of S plane, and for a minimum phase system, all the zeros also in the left half of S plane. Whereas for a maximum phase system, all the zeros are in the right half of S plane. Next, for a mixed phase system, some zeros in the right half of S plane, some zeros in the left half of S plane. So here, right, left half of S planes we are talking about. In discrete time case, we are going to talk about unit circle, inside unit circle, outside unit circle. So the same thing. So first of all the poles must be inside the unit circle. Inside the unit circle. That implies stable. Stable system. Next, what we have to see? Minimum phase system. In the minimum phase system, all the zeros are inside the unit circle. Inside the unit circle. So for a minimum phase system. Second one, maximum phase system. For a maximum phase system, all the zeros in the outside the unit circle. All the zeros are outside the unit circle. Outside the unit circle. Last one, mixed phase system. mixed phase or non-minimum phase, we can say. Mixed phase. Mixed phase system means some zeros in the outside the unit circle, some zeros inside the unit circle. Some zeros outside and some are inside unit circle. Unit circle. So this is the definition of minimum phase, maximum phase, mixed phase. So this is the first classification of digital system. So let's say I will give you one question. You can understand what system it is. H of z is equal to 1 plus 7 by 2. Let's call it as question number 1. Z inverse plus 3 by 2 z power minus. Then the system is option minimum phase, maximum phase, mixed phase, zero phase. Which kind of system it is? So for that we have to see what are the zeros for it. So what is h of z they have given? H of z is equal to, so if I take a z power minus 2 common out, then this is z square plus 7 by 2 z plus 3 by 2 by z square. So even if I simplify it, 2z square plus 7z plus 3 by 2z square. So I want to calculate zeros. What are the zeros? To calculate zeros, so I have to equate 2z square plus 7z plus 3 is equal to, so this is 2z square. So I can write this as 6z plus z plus 3. 2z common out, z plus 3, 1 common out, z plus 3. If I take z plus 3 common, then this 2z plus 1 is equal to. So what is the zeros here? Minus 3 minus 1 by 2. So if I observe carefully, so many people will say minimum phase. So they think that both the zeros are in the left half of its plane. But it is not about the S plane, it is about the Z plane. So in that Z plane, what we have to see, where the zeros are located, whether they are in the inside unit circle or outside the unit circle. But if you see, minus 3 is the outside unit circle, minus 1 by 2 is inside unit circle. So outside is 1 0 is there, inside 1 0 is there. So it is a mixed phase system. It is a mixed phase system. Clear? Take it. Next, classification of filters. Based on input output relation. Input output relation. Based on input output relation. So first, FIR, that is finite impulse response. This is also called as moving average filter. Moving average. So in this, output depends on present output depends on present and past in present and past in. So if y of n is there, it is having a relation something like this: x of n plus a1 x of n minus 1 plus a2 x of n minus 2 and so on. So these are the past in. So whenever if input output relation looks like this, then it is a FIR filter. Next, IIR filter, infinite impulse response, or we can say autoregressive. Autoregressive filter. So in this one, present output depends on present input and past outputs. Past output. So it looks like this: y of n, present input x of n, and no past out inputs. So it is going to be plus b1 y of n minus 1 plus b2 y of n minus 2 plus and so on. So present input, past outputs. Then we can call it is a IIR filter or autoregressive filter. And there is another filter, ARMA filter, ARM, autoregressive moving average filter. Moving average filter. So in this, both the kind of things we have to say. So that means present input has to be there, past inputs has to be there, past outputs has to be there. Then we can say ARMA filter. Present output depends on present and past inputs and past outputs. Past outputs. So y of n looks like this: x of n plus k1 x of n minus 1 plus a2 x of n minus 2 plus and so on plus b1 y of n minus 1 plus b2 y of n minus 2 plus and so on. So this kind of input output relations are there, then we can call this as a ARMA filter. Okay. So just introductions only we require, not much deeper. Question number h of z is equal to 1 minus 0.8 z inverse by 1 plus 0.8 z inverse. It represents it represents option A, Autoregressive filter. Option B. Moving average filter. Option C. ARMA filter. Option D. FIR filter. Actually, FIR filter, moving average filter, both are same. But so on that basis, that may not be the correct answer. Let's see. H of Z is given. So H of Z is nothing but Y of Z by X of Z, right? H of Z is equal to Y of Z by X of Z, which is given like this: 1 minus 0.8 Z inverse by 1 plus 0.8 Z inverse. So by cross multiplying that, Y of Z plus 0.8 Y of Z into Z inverse is equal to X of Z minus 0.8 X of Z into Z inverse. So by taking inverse Z transform on both sides. So this is Y of n plus 0.8 Y of n minus 1 is equal to X of n minus 0.8 X of n minus. So if you observe carefully, present output Y of n is equal to present input minus 0.8 past input minus 0.8 past output. So here we are having present input, past input and past output. So it is a ARMA filter. ARMA filter. Here, take it. Classification of filters based on the frequency response. So here we usually use h of e power j omega. This is the DTFT or h of z. H of z. I told you testing range of frequency. Omega, that is 0 to pi. 0 to pi. Where 0 indicates low frequency, pi indicates high frequency. High frequency. In the similar way, what is the testing range of Z? That is 1 to minus 1. This is on the unit circle only. So suppose if I take unit circle, so this is going to be omega is equal to 0, omega is equal to pi. So Z is equal to 1, Z is equal to minus 1. Minus 1. So in this unit circle, this is the path what we have. Upper half of the unit circle. Okay. Now this 1 indicates low frequency because that is corresponding to omega is equal to 0. This minus 1 indicates high frequency. High frequency. Suppose in between I want then Z is equal to J. Suppose if I take Z is equal to J, that is indicates mid frequency, somewhere mid frequency. Okay. Take it. Identify the filter nature of following discrete time system. Discrete time. So let's see the first question. Y of n is equal to x of n minus x of n minus. So for this system, is it a what kind of filter? High pass filter, low pass filter, band pass filter, or band stop filter? These kind of things we have to check. So to check this, we require maybe h of e power j omega or h of z. So I will always go with the h of z notation. Let's Z transform. So what is y of z is equal to x of z minus x of z into z inverse. So if I take x of z, so what is h of z? Y of z by x of z. If I take x of z common, 1 minus z inverse. This is nothing but 1 minus 1 by z. So there is nothing but z minus 1 by z. Z minus 1 by z. So finally I got h of z is equal to z minus 1 by z. Now I want to test the system. What kind of filter it is? So I told you z is equal to 1 indicates the low frequency, z is equal to minus 1 indicates the high frequency. So let's see. At z is equal to 1, what is h of z? 0. At z is equal to minus 1, then what is h of z? Minus 1 by minus 1, that is nothing but 2. So here z is equal to 1 is a low frequency, it is not allowing. Z is equal to minus 1 is a high frequency, it is allowing. So I can say this is nothing but high pass filter. High pass filter. Take it. Y of n is equal to x of n plus x of n minus. What kind of filter it is? Let's y of z is equal to x of z plus x of z into z inverse. So what is h of z? Y of z by x of z, that is 1 plus z inverse. So 1 plus 1 by z, that is z plus 1 by. At z is equal to 1, low frequency. What is h of z? At z is equal to minus 1, high frequency. H of z is equal to 0. So it is allowing low frequencies, not allowing the high frequencies. So it is a low pass. It is a low pass filter. Third one, y of n is equal to x of n minus x of n minus. What kind of filter it is? Let's y of z is equal to x of z minus x of z into z power minus. Then what is h of z? This is y of z by x of z, which is 1 minus z power minus. That is z square minus 1 by z. So let's say one by one. At z is equal to 1, low frequency. What is h of z? That is 0. At z is equal to minus 1, that is high frequency. H of z is again 0. So at low frequency its value is equal to 0, at high frequency its value is equal to 0. In between, let's say at z is equal to j. So mid frequency. What is h of z? This is minus 1 by minus 2. So I hope you understood. So it is not allowing low frequencies and high frequencies, but it is allowing mid frequencies. So what kind of filter? Band pass filter. band pass filter. Third one. Fourth one. Y of n is equal to x of n plus x of n minus 2. What kind of filter it is? Again, h of z I am trying to find out. Y of z is equal to x of z plus x of z into z power minus 2. Then what is h of z? Y of z by x of z, which is 1 plus z power minus 2. That is z square plus 1 by z. So at z is equal to 1, what is h of z? That is 2. At z is equal to minus 1, what is h of z? That is also 2. So at low frequencies, high frequencies, both are allowed. What about at mid frequency? At z is equal to j, then h of z is equal to minus 1 plus 1 by minus 1, which is 0. So it is allowing high frequencies, it is allowing low frequencies, but it is not allowing mid frequencies. So it is a band stop filter. Band stop filter. Question number 3. A system transfer function h of z has impulse response h of n, comma, h of 2 is equal to 1, h of 3 is equal to minus 1, h of n is equal to 0 elsewhere. Then it is option A, low pass filter, option B, high pass filter, option C, band pass filter, option D, band stop filter. Band stop filter. So listen here. Impulse response h of n is existing only at 2 and 3. So we can write h of n is equal to, like, at 2 we are having 1, so delta n minus 2. At 3 we are having minus 1, minus delta n. So this is what h of n. So once we know h of n, we can write h of z, that is z power minus 2 minus z power minus. So z cube if I take, then this is z minus 1. So this is what h of z. So at z is equal to 1, low frequency, what is h of z? 0. At z is equal to minus 1, h of z is equal to minus 1 by minus. So this is 2. So it is allowing high frequencies but not allowing low frequencies. So it is a high pass filter. It is a high pass filter. Final one, the filter what we have to discuss is all pass filter. All pass filter. You know, all pass filter means it will allow all the frequencies and it is going to change the phase for different frequencies. That means different frequency components having different phase. That's what the meaning of it. So that's what the all pass filter. So in the continuous time case, you might know this. For an all pass filter, the pole zero location has to be in such a way that is, suppose in a continuous time case, all the poles has to be in the left half of its plane, all the zeros has to be in the right half of its plane. That's the one condition. Number of poles is equal to number of zeros. That is another condition. Next, and they have to be symmetrically located with respect to origin. So in that condition only, that will act like a all pass filter. So exactly the same thing here also. Number of poles is equal to number of zeros. Number of zeros. All the poles must be inside the unit circle because stable system. Inside the unit circle, and all the zeros must be outside the unit circle. Must be outside the unit circle. Must be outside the unit. Next, there we have seen symmetrical location, but here in the discrete time case, it is conjugate symmetry with respect to each other. Poles and zeros are poles and zeros are conjugate symmetry. Conjugate symmetry. Conjugate symmetry with each other. What do you mean by that? Suppose if, let's say, 0 is equal to z, then what is the pole for this? Is nothing but 1 by z conjugate. Conjugate reciprocal. Conjugate reciprocal to each other. Not symmetric. Conjugate reciprocal. Sorry, you can take this one. Conjugate reciprocal. Conjugate reciprocal means this one. Suppose, let's say, 0 is equal to 2, better 0 has to be outside, right? 2 at an angle 45 degrees. Correspondingly, pole has to be 1 by 2 at an angle 45 degrees conjugate. Then this is 1 by 2 minus 45 degrees. So it is 1 by 2 at an angle minus 45 degrees. The pole must be inside. The pole must be 1 by 2 means inside, minus 45 degrees has to be there. So this is what the all pass filter is. Take it. Question number 4. For an all pass filter, h of z is equal to z inverse minus c 1 minus a z inverse. Okay. Then B is option A, option B, A conjugate, option C, 1 by A conjugate, option D, 1 by 1 by. So here so many people do mistakes, but don't do any mistakes. Try to understand first. Rewrite the h of z. What is h of z? Z inverse minus C by 1 minus A z inverse. So if I take Z inverse common, 1 minus B Z by Z minus A. So here, what is pole A? What is 0? 0 is equal to 1 by B. This is pole. Pole is equal to A. So what should be the relation here? 1 by B 0 is equal to 1 by A conjugate. So B is equal to A conjugate. So option B. Clear? Take. So with this, we can conclude all pass filters and the digital filters. So with this, I can conclude the signal sound system topic. And thank you. All the best.